ready to get started. We have got a lot of practice, I guess. Learning some new stuff. And when we left you off last week, we talked about, the shortcut technique for finding derivatives of functions. And that's kind of where I'm going to continue from. Before I get stuck into that and do as many examples as I can, because that's just, as far as I can tell, that's the best way to learn how to do these, is I want to get you some notation. So let's do a basic polynomial. I hope polynomials now are like second nature to you. Right. That's the symbol for the derivatives, and we say that out loud as f dash x. So f dash of x is power roll. Multiply by the power, reduce the power by 1. When it's something like a multiple of x's, just do that, and when it's a number, just give you 0. That is one notation for derivative. If your function was written as y equals the same guy, then your notation for derivative would be y dashed. Bubbles around these guys or something. There we go. If your function was written as y equals, you can also write the derivative using this notation. And you say this out loud as dy by dx. So there is no difference to those three questions, right? They're the same answer, they're the same starting function, but sometimes you call the derivative y dashed, sometimes you call the derivative dy by dx. There are uses for why we need three notations, and we won't get into that today, but there's a good reason why they have more than one notation. Now you can also have essentially y equals 3x cubed minus 2x plus 1, and y equals 3t squared minus 3t cubed minus 2t plus 1. Mathematically, those are equivalent. They have, one day I'll get this right, they have the same answer. So the variable that gets used is typically x, but there's no reason in the world why you couldn't differentiate a function using t. In fact, if you're using this notation, the derivative might be called dy by dt. So just be aware of the different notations that are sometimes used to mean the derivative. The most common is f dashed, but you might do y dashed, you might do dy by dx. The variable may not be x, it may be t or w or u, but that doesn't change anything, right? The answer's the same, the notation is similar. Okay. So that's my one candidate for a simple polynomial. The next guy we're going to look at, again, this is an overlap from Friday, is how you deal with radicals, square roots and cube roots. Well, the first thing you should do is to rewrite them as fractional powers. Oops. That says x to 2/3. So if you write them as fractional powers, you can use the power rule, which is multiply by the power and reduce the power by 1. Multiply by the power and reduce the power by 1. And we talked on Friday about an important part of these questions is what you do to your answer to make it look standard. Right, standardize the answer so that everybody ends up having essentially the same answer. I call that process style points. So in this case here, our derivative has negative fractional powers. We want it to look like the original. The main rules are, number one, make it look like the original. That's the first rule. Rule 2, factor the heck out of them, if you can. And rule 3 is, if there's trig functions, look for identities that might make it nicer. So in this case, a negative power can be rewritten as a fraction on the bottom, positive power. We're comfortable with negative becoming positives, right? And then all fractional powers can be rewritten as radicals, like the square root of x in this case, and the cube root of x in that case. Can you kind of remember doing on Friday questions like that, right? Square roots, cube roots. Moving on to our third category, which is rational functions, essentially fractions. But pretty simple fractions, just fractions that look like that. Okay, let's see if you can remember. What do you rewrite 4 over x cubed as so I can use a power rule? So what does this become? I need to write this in a format that will allow me to use the power rule. So how will I rewrite this?
4x to the negative third.
There you go. Now you can do your power rule. Multiply by the power and reduce the power by 1. Notice it's negative 4. If you take 1 away from negative 3, you get negative 4. And now we move into make it look pretty, style points. In this case, you get that. Now, if you get a question and it starts off life looking like that guy, right? So that's the way the question is given to you. Then there underneath is its answer. Do you see that in that particular question, isn't the answer x to the negative 4, because does it not look just like the original, right? So if the original was differentiate 4x to negative 3, your answer would just be negative 12x to negative 4. Whereas if your question started life as a fraction, you see it now needs to end as a fraction. So be aware that the rule, the major rule, make it look like the original, is your go-to guy, right? What do you give me? I'll give you an answer that looks like it. Kind of say that to yourself. Are we good with that one? Yep. Next fella is exponentials. Oops. And if you want to differentiate this guy, you get that. There's not an awful lot to differentiating exponential functions. Agreed? At least the simple ones like that. So far, so good. So that's kind of summary of Friday. We did most of this on Friday. So now we're moving into a batch of questions that don't fall into nice categories. I'm calling them complex expressions. Here are some examples of them. Ugly fraction, weird FOIL, exponential that doesn't have an X in it, weird radicals, right? That's kind of where we're going to work on now. And there are lots and lots of variations that we could have done here, but this is just like a taster of it. Then we're starting a new page. Right. This is not the only way algebraically to do what I'm about to do. But this is one of the ways. I cannot differentiate this fraction the way it's written. So I'm going to rewrite it as a multiplication. Basically, instead of dividing by x to the 4, I'm going to multiply by x to the negative 3. X to the negative 4. Got to focus today. Instead of dividing by x to 4, I'm going to multiply by x to negative 4. Well, this guy times this guy gets you 7x to negative 1. This guy times this guy gets you negative 2x to 0. And this guy times this guy gets you x to negative 4. And I'm going to leave that one alone. And I'm going to leave that one alone. But this guy in the middle could be written in a better way. What is negative 2x to the power of 0 the same thing as? Well, let's think of it this way. What's x to the 0? What's that worth?
Just 1?
Right, so isn't that just negative 2? You comfortable with that now? Now, once you've got it separated into individual pieces, the power rule can now be applied. So the derivative, well, multiply by the power and reduce the power by 1. The numbers don't get you anything, so I'll just put in a plus 0 there. And this guy, you multiply by the power and then reduce the power by 1. Now, if you think that that's good, then you've not paid attention to what I'm saying about style points. Would you agree that these do not look like the original? All you need to worry about is making it look like a fraction. What you don't need to in this stage worry about is adding or subtracting these two fractions together to make one fraction, right? So you don't need to worry right now about that. You just need to realize that you need to be, you need to have fractions. Now, I went and said that there was two ways, at least two ways I can think of, in which to deal with this question, right? So this is the question back again. The other method is to split the fraction into 3 pieces. Each piece on its own is divided by x to the 4. And then when you simplify this one, you get 7x to negative 1. When you simplify the middle one, you get negative 2. And when you simplify the last one, you get negative 4. You see that you end up with the same answer as we did the first method. I just think the first method is cleaner, but that's just my brain. Right, the first method, make this a negative 4 and multiply through. Second method is split it into 3 fractions and get each one in its own. Maybe you like this method better. That's totally understandable. If you do, you would do it that way. If you like this method, of course, then that would be the one you would choose. Mathematically, we don't care. We're both correct. They both get the right answer. Okay, so far so good. Doing a bit of algebra, a bit of power rule. That's kind of the theme. So I'm going to see if I can find an example of that that's a little bit harder. So question 7 in the homework looks something like this. So this is similar to the one I just did, but really an extra level degree of of being difficult, right? And one of the problems is that 8 on the bottom is a little bit harder to deal with than just having the power of x. And secondly, there's a square root involved instead of everybody being whole number powers of x. So both of those things are going to have to get fixed And so I'm going to show you how I would deal with it. And I'll do it quite slowly. So like one step at a time. I hope it was obvious that you're going to call the square root an x to the half. You should do that with everything, right? Cube roots and fourth roots and whatever, right? In this case, the second method that I showed you, which is split the thing into separate fractions, each one divided by, in this case, 8x squared, is a better method than the multiplication one I showed you, in my opinion. And this guy, you can now do. Side issue. In math, if you have an x to the a on top and an x to the power of b on the bottom, and you want to rewrite it as a single power of x, the rule is x to the top power, take away the bottom power. Can you remember that rule? Top power, take away bottom power. I'm going to use that rule now. You wouldn't normally write this down, but I am. That's essentially the working. 1/2 take away 2 is -3/2. Do you see how ugly that answer is? But that's what it is. Now, this one. One take away 2. That simplifies to 1/2 x to -1. Are you comfortable about how we took the original fraction and have separated it into two powers of x, in this case -3/2 and -1? We can now differentiate. Multiply by the power, which I believe is -27/16, and then reduce the power by 1. Multiply by the power, and then reduce the power by 1. Negative power comes downstairs and becomes a positive. Negative power comes downstairs and is a positive. Fractional powers can then be written down as a radical. And 5/2 gets you the square root of x to the 5. And this fella is good. Have you noticed how much algebra is involved in differentiating ugly functions like this? Converting things into fractional powers, dividing by separation. Using this rule to find out what that particular combination gives. Differentiation was actually only that line there. That was the only line where I actually did anything to do with differentiation. Everything up to here was algebra. Then I differentiated, and everything after that was algebra. Rewriting negative powers as fractions, rewriting fractional powers as radicals. So knowing the power rule is only one piece of the puzzle. You've got to know how to turn things into a form that lets you use the power rule. And then when you're finished, you have to take your answer and figure out how you're going to rewrite it in its standard pretty format that everyone is expecting. Here's another one of those weird fractions. Variable is going to be called z. And so here's the convention. Z is a variable because this is a z, right? So we know that anything that is z is just like our x's. Any other letter of the alphabet that appears, A's, B's, and C's, you will treat them like numbers, like it was 5 or 5z or 5z squared, right? You're just going to treat them like numbers. Now, since this one has just a single power, I'm going to go to my first method, which is multiply everybody by z to -2. You can also use my separating the thing into 3 fractions method, and that will work equally correct. Now, in this case, you get that. This guy times this guy gets you a -1, and this guy times this guy essentially gets you 1, because z to the 0 is 1. And I'm using the rule that when you multiply powers, powers of z together, you just add the powers, the exponents. Now I can differentiate. -2a, right? So multiply by the power, reduce the power by 1. Multiply by the power, reduce the power by 1, and numbers get you nothing. And to finish, style points. Are we good? Any questions so far?
So when you multiplied cz squared by z to the -2, you got 1.
Mm-hmm. And so how did I get that?
Oh,
Yeah. So if you multiply them together, the rule is you add the powers, and z to the 0, or anything to the 0 for them is 1. So it's where the 1 came from. That makes sense? Right. Let's try a guy with this look to it, right? So I'm going to do a version of my guy here, but I'm going to do 9. And we've got a change in variable, it's now w. When the guy on the bottom is a single power, right? So it's just z squared. It's not 3z squared or 5z squared, but just z squared. Or it's just the square root of w as it is here. Then I tend to do it the first way. So that's going to be 6w squared, 4w plus 2. And now I'm going to skip a line of working. The square root of w is a half power, right? So that's w to the half. So when it comes up here, you multiply by w to the -1/2. Are you comfortable about how that square root has changed? Right, w to the half on the bottom, w to the -1/2 now on the top. Now, when you multiply through, 2 and -1/2 get you 1.5, which is 3/2. 1 and -1/2 gets you 1/2. And 2 times that gets you that. So the derivative is again the power rule. If you multiply these together, you get 9, and then you reduce the power by 1. Multiply these together, you get -2, and then you reduce the power by 1. Multiply these together, you get -w, and then you reduce the power by 1. And style points, turn that into square root of w. Okay, what do you think I'm going to do with this guy and this guy? Because something else has to be done.
Put them on the bottom.
Okay. And now I can turn that first one into a square root, and that second one into the square root of w cubed, and we are finished. So I'm not sure when you signed up to do Calc 1 that you realised you were signing up for an algebra class, because that's, I mean, if I'm looking at how much skills I'm using an awful lot more algebra skills than I am, you know, differentiation, right? I'm only differentiating using one rule called the power rule. Everything else that you see in front of you here in this question is some kind of manipulation using algebra rules. So being good at algebra is a good way of being good at calculus. Okay, I think we can cross off our list. Guys that look like that and that. So let's look at guys that look like this. Weird foils. Okay, first time, maybe the first time we've seen it. I can't remember if I did anything like this. But what would you expect to do algebraically to get this in a form that would let you differentiate?
Expand it.
Yeah. What I call FOIL, but expand it is correct. So F O I L would FOIL it. Now, 2 square root of x's, actually, I'll write this line down. You wouldn't normally do this, but 2 square root of x's times another 2 square root of x's gets you 4, and a square root of x times a square root of x gets you an x, so you actually get 4x. That's the F part of FOIL. Now, what does it all look like? Well, 2 square root of x times -1 is just -2 square root of x's. If you want to do the I, 1 times the square root of x is plus 2 square root of x's. And then the L, well, in this case, plus 1 times -1 gets me -1. These two kill each other off. And then you say, wow, I wasn't expecting that. That horrible mess is actually just 4x minus 1 when you FOIL it out. And differentiation now becomes very straightforward. And would you agree there isn't any style points, because that's as good as that answer's ever going to look. Let's do a homework question. Question 5 looks something like this. So I'm going to FOIL it, distribute it, by writing it like that. This time I'm going to be a bit quicker. 2t times 2t gets me 4t squared. 2t times -3 gets me -6t. -3 times 2t gets me another -6t. And -3 times -3 gets me plus 9. So I have 4t squared minus 12t plus 9. And no, I do not get 4t squared plus 9. If you think you know a shortcut for making that answer, right, for following that out, it isn't 4t squared, right? 2t times itself plus 3 times 3. Do you notice there's a minus 12t? Some people still do that shortcut. I do not know where they got it. I wish they could forget it, because it isn't right. Right? You end up with 3 terms if you do it correctly. So you differentiate it. Power rule, 8t, take away 12, and you don't need to do style points. That looks perfectly fine. So I guess style points are done. Any questions so far? We certainly have covered a lot of situations, haven't we? But there is a kind of theme to it, right? And all of them rewrite it in such a way that you can do the power rule. That seems to be the theme. Once you've rewritten the thing so that you can do the power rule, you then differentiate it, and then you make it look pretty. Right? So that would be the kind of the go-to method. So now we're going to look at some, oops, cross that off my list. Now we can go and look at more complicated versions of this. So I'm going to start with a nice guy, just to get the ball rolling. Differentiating 3e to the x gets you 3e to the x. So how do you differentiate that guy? Okay. Well, the algebra I'm going to use looks like this. If you multiply two powers of e together, don't you add their exponents, right? X add 2. So I'm basically breaking this apart into its constituent pieces. So e to the x add 2 is e to the x times e squared. And I'm just going to stick the e squared on the front because e squared is a number, isn't it? It's like 2.7 times another 2.7, right? It's about 8 and a bit, right? Now, when I write it like that, and I realize that e squared is just a number, because that's all it is, isn't this the same as 3ex, 5e to the x, 2 million e to the x? Because I can get its derivative. And the derivative of this guy is e squared e to the x, right? Like 5e to the x differentiates 5e to the x. And then to make it look pretty, can't I just join these two guys together? And then you're going to say, God, that was a long way to get back to where you started. The derivative of e to the power of x add 2 is just e to the power of x add 2. Isn't e to the x a nice function? Now, suppose somebody stuck a 5 there. Well, wouldn't there be a 5 here, a 5 here, a 5 here, and a 5 here? Do you see it really doesn't do much damage to your answer at all, does it? You still end up with the guy that you started with. You cool with that? Now, e to the x, some versions of e to the x don't end up being the guy you start with. The ones you've met so far and the ones that you will meet in 3.1, that will be true. But later on, you'll see that there are different versions of e to the x that don't have that. For instance, e to the power of sine x. The answer isn't, its derivative is not e to the sine x. Well, actually, it is e to the sine x, but it also has some other stuff, right, which you don't normally have. So bear that in mind. But right now, that rule works quite well. Any problems? We cool? What would the derivative of e to the t minus 3 be?
Et minus 3.
Yeah, that's what I'm getting at. Isn't e a nice function to differentiate? Right. Right now, it's a nice function, so we will leave it at that. Okay, I want to cross it off my list then. Are we good? Right. So the next big chunk is a catch-all phrase, which is essentially find the equation of a tangent line and other things. So let me kind of tell you what's going to be in applications, because there's a lot of things. So first thing we're going to do is have questions where they ask us to find the equation of a tangent line. So an example of that, Could be question 12. So we're going to find the equation of a tangent line. And there will be a curve, in this case, x plus 7 over x. And at some point, in this case, 7, 8. So the standard question is, find the equation of a tangent line, insert function here, at insert coordinates of point here, right? So this function will change, and obviously the point that you find the equation of the tangent line will also change. So for this type of question, you can pretty much set up a little step 1, 2, 3 thing. Step 1, find the derivative. Okay, so that's the first step. So here is the original function. I need to write it in a format that is going to allow me to use the power rule. I can't do it with this guy. Any volunteers for how to rewrite this so that we can use the power rule?
Rewrite it as x plus 7 to the negative 1.
You all comfortable with that? So now we can do the derivative, which is 1, multiplied by the power, and then reduce the power by 1. And then style points. Now, another good reason for doing style points is that when you find the value of a derivative at any given point, it's normally much easier to do the answer as an exact value when it's written like this, as opposed to written like this, right? So step 1, find the derivative. Step 2, find m, which is the slope of the tangent line. At whatever point happens to be in the question. So we're going to find the slope of the tangent line at 7, 8. Well, that means I'm going to find the derivative when x is 7. And so it's going to be 1 take away 7 over 7 squared, which is 1 take away 7 over 49, which is 42 49ths. And now I'm going to check that on my calculator. 1 take away 7 49ths. And we get that, and then do math and do fraction. And the answer is, let me do that again. 1 take away 7 49ths. That's better, right? You get that guy. Math number 1, and I get the answer 6/7. I'm not wrong, I just didn't notice that I could simplify it. But you see, it works quite well. Can you imagine trying to do 7 times 7 to the power of -2? Couldn't you end up with some weird looking answers that aren't easy to work with? So I now know the slope of the tangent line. Final step, step 3. Use the point slope equation, which is this guy. To get the equation of the tangent line. So it's going to be y take away 8, the slope, x take away 7. Distribute the 6/7. 6/7 x, take away 6. Add 8 to both sides. And you are finished. There is the equation of your tangent line. In a lot of these questions, there's a second part which basically involves Desmos. And what you would do is you'd plug that in as y1, and you'd plug this guy in as, you know, your second equation. And if it works correctly, shouldn't you get a nice tangent line meeting a curve? And shouldn't it meet at 7,8? Well, that's the plan. Do I have Desmos set up yet? Okay, I will do that. Bear with me for a few moments. Oh, come on, computer, stop being a pain. There we go. So I'm going to put in the original function and the equation of the tangent line. And I want to, hopefully, are you looking at Desmos right now? Oh, good. So I want those two to meet at the point 7,8, like a tangent should meet, right? Not cutting it, but just glancing it and moving on. So there's an x plus a 7 over x. Pretty ugly function. And then y equals 6/7 x. Take away 6. Okay, and what's the point I'm looking for? 7,8. Oh dear. And the oh dear was because I didn't write down the right equation. That was the equation of the tangent line. And it's now not an oh dear. Would you agree that that is a really nice fit? There's the point we're interested in there, right? Isn't that a nice tangent line? Now, if you had put in the mistake, like, you see how that one doesn't make a tangent line? It's certainly not a tangent line at 7,8. So, in a test, couldn't you use Desmos to check your answer? Draw the original, draw the tangent line. If everybody meets, if I don't know, pulling that doesn't help any. I'm convinced. Are you convinced? I mean, one of the other ways is, do you notice that when you zoom in, you can't tell a difference anymore? That's one of the properties of a tangent line, is that it is so like the curve, you know, like a microscopic level, that you can hardly tell the difference. I'm pleased that one worked out good. Any questions? I'm doing such a fantastic job that you don't have one problem, right? Everything's so obvious. I'll stop nodding your head, Vanessa. God. Right, I'll assume then that at least it's only minor problems, nothing you feel that worried about asking. Okay. So equations of a tangent line basically follow: find the derivative using whatever algebra you need to get there, make it look pretty. Find the slope by taking the equation of the tangent line and plugging in whatever the x coordinate is, 7 in this case. And then I am going to pause for a minute. And blah, 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 blah. Try to cover up noises. There. Whoever's having that conversation doesn't need to hear us, right? Or we don't need to hear them. So, okay. So where was I? Yes. Get derivative, evaluate it at the x coordinate 7, use the point slope equation. You got it, right? Now, at this point, I'm going to introduce you to a new guy. And let's find the equation of a normal line. So I'm going to try and show you what a normal line would look like. Can you imagine that was our curve? Y equals f of x. And imagine that this was the point P that we're interested in, right? This red line is our tangent line, right? And we've done that. Where's my green? A normal line is at right angles to the tangent line. So this is what a normal line looks like. And I'm going to pretend that P is now there, right? You see what a normal line does is different from what a tangent line does. Now, the good news is that it's virtually the same process with one important change. You will still do step one exactly the same. Done, right? Step two is where the change happens. Once you find this slope, right? So you still have to find this one. You then have to find the slope of the normal, Mn, right? So that's MT is the slope of the tangent line. Now we need to find the slope of the normal line. A tangent line and a normal line are always going to be at right angles to each other, right? That's the way they work, right? So if the tangent line changes, you see the normal line will follow it. There is a formula for finding the slope of a line that's perpendicular to someone. There's a vague chance that somebody might even be able to tell me. Does anyone know how to find the slope of a line that's perpendicular to some other line? So perpendicular to 6/7 here. Now, you might never have heard of it, so I don't think it was kind of fair to tell you. So here it is. It's a negative reciprocal. If you want to hear it as a word, it's a negative reciprocal. Turn this guy upside down and make him negative. That guy is always going to be perpendicular to that. So see if the slope was a half, the tangent line will be -2. If the first guy is 3/7, the other guy will be -7/3. If the first guy is -5/50, the other guy will be +50/5. Do you see how it works? Turn me upside down and stick a negative. Now, once you've got that, you use exactly the same formula that you did in step 3, but won't this number now become -7/6, right? Because you're going to be finding the slope of a line that has, the equation of a line that has this slope and not that slope. So although it's the same equation, won't the value of the slope change? And so you calculate this one and you get a different answer. We'll continue this tomorrow because time up. So make sure you put your last name down, and I'll hang about for questions. Otherwise, I'll see you tomorrow. Bye-bye.
Thank you.
You're welcome.
Thank you.
You're welcome. Okay, who's got the questions first? Anybody?
I have a question about something that was on the last quiz thing.
Okay.
So on question 12, we were supposed to estimate the value of each derivative by just looking at a graph.
I'm going to look at that question that doesn't, I'm not saying I can remember it, which I don't. Okay, let me have a look at it. I'll do yours because the questions will change. Hold on for a moment. Let's see, Jason. W. Okay. And question number, what were you talking about?
It was 12. I think.
Okay. So, well, okay. Right, and it says use the given to estimate the value of each derivative. So you kind of do an eyeball, and as long as it's in the general vicinity, it's right. Actually, you got the question right, so whatever it was, you were doing it right.
Okay, yeah, I wasn't really sure how accurate it was supposed to be, so I
You're
printed
not
out,
going to be accurate. Yeah, you
Okay.
know.
Yeah, I printed out the page and used a ruler to like
Oh, that
sketch
was
out.
clever. Yeah, there's a lot of wiggle room in that. So, I mean, if the right answer is 3, anything between 2 and 4 would be fine.
Mhm.
If
Okay.
the right answer was -7, anywhere between -6 and -8 would be fine. So yeah, you're not. There's no way in the world you're going to get any degree of accuracy from that kind of sketch.